Welcome to this video where I'll be presenting proofs of these two famous 19th century math conjectures, which most of the academic math world still consider to be open and unproven. But to understand this video, you don't need to be a mathematician, and in fact, you don't need to have much of a math background at all, because everything presented here will be simple. The only thing you need to know to follow along is you need to know how to count. You need to know how to add, subtract, and multiply. No division needed. You need to be able to think and reason logically. Now this is important. You need to have an open and objective mindset. Because if you come into this with the attitude, proof's my ass, stop the video and go back to pulling wings off butterflies. And you need to want to have fun, because we're going to have lots of fun playing with numbers. Hi, I'm Jabari Zakia. Here's a little bit of information about me. Please check out my academia.edu page at the bottom, because it has all the papers I'll be speaking on in this video, and a lot of other good stuff too I think you'll find interesting. In 2019, I started writing and first released this paper on the infinity of twin primes and other k-tuples. It's available for free to read and download at the two links listed below. This video contains the contents of that paper that I get to actually present in a much more user-friendly manner. But I couldn't cram all the stuff in that paper into this video, so I encourage you to please read the paper afterwards if you want to know the full story. Let's start with Polignac's conjecture. Alphonse de Polignac was a 22-year-old French university math student when in 1849 he conjectured, for any positive integer n, there are infinitely many prime gaps of size n. In other words, there are an unending number of consecutive prime pairs which differ by any even value, 2, 10, a million, a googolmillion. And the reason they are even is because, except for 2, all the primes are odd, and whenever you subtract or add two odd numbers, you get an even number. And the twin primes conjecture is just the specific case for prime pairs that differ by 2, such as 11 and 13 and 17 and 19. And a k-tuple is a specific grouping of consecutive primes, where k is the number of primes in the group and n is the distance between the first and last one. We're only interested in prime pairs, two consecutive primes that differ by any even number. A more interesting question for us will be, can there be a finite number of prime pairs of any size n? Such as, can there be a last pair of twin primes, or for any other gap size? Let me now explain my approach to visualizing this problem. The first thing we need to do is understand the problem domain. To me, this is a discrete math problem, sort of like a Sudoku. All the numbers involved here are a relatively small set of integers, and Sudokus are purely logic problems. You don't need to do any computations. Given a starting grid, the rules totally determine how the other numbers must be distributed. I'll show the prime gaps puzzle is similar to a Sudoku. I'll first show how to develop the rules for their distribution, and once we know them, we can determine the distribution for all possible prime gaps. By brute force, we could try to generate all the primes so we could empirically see and count all their different gap sizes, but that has obvious limitations. What would be better is to create a way to generate just enough primes to allow us to characterize their gap structures in a mathematically consistent way that scales as we go up the number line. Well, it just so happens I had created the right mathematical tools to do this. So what I will show here is we can create a consistent, deterministic, and scalable mathematical framework that will systematically establish the structure of the primes and thus their gaps that will show with absolute certainty there are an unending number of prime gaps that differ by any even value n. The mathematical framework I've developed I holistically call prime generator theory, which is based on prime generators, which, as the name implies, generate all the primes. And each prime generator has a characteristic prime generator sequence, which is the sequence of the gap sizes between the generator residues. And the residues exist as modular complement pairs, which create a mirror image modular complement symmetry of the generator sequence. This is of fundamental importance in establishing the distribution properties of prime gaps. It's this modular mirror symmetry that scales to establish how the prime gaps occur over any range of numbers. Let me now describe conceptually what our mathematical framework is doing. We start with the simple number line you learned in elementary school. Now our goal is to find all the primes. So what we do is break the number line into finite groups of numbers of even size. The size of the groups I call the numerical bandwidth of our process. Now our bandwidth can be any even number, but we'll only be using special numbers whose values are the primorial of primes. We do this to reduce the number space that the primes exist within, that is, the percentage of all numbers that can contain primes. Now residues are special numbers that act as prime generator frequencies, like on a radio. And the spacing between the residues is well defined, just like the spacing between stations on a radio. So we move from one group to the next, looking for larger primes that the residues will generate. And when we write out the values for each group, this will produce a table of the minimum number of values that can possibly be prime for a given bandwidth size. To see these concepts in action, we start with our number line. This is a one-dimensional representation of the entire number space. To find all the primes, we have to go through 100% of all integers to identify them. We can reduce the prime number space by breaking the number line into even-numbered finite groups. The first even number is 2, which is also the first prime, and also the value of 2 primorial. So the first way we can break up the number line is in groups of 2, which we write in a two-dimensional form like this. We've now divided the number space into the evens and odds, and all the primes greater than 2 are in the odd number space, which is 1/2 or 50% of all numbers, and they all have a residue of 1 here. The next primordial grouping is 3 or 6, but before showing it, I would encourage you to draw the groupings for bandwidth sizes 3, 4, and 5 to see for yourself what happens with the primes in those cases. This is the picture for the 3 primordial numerical bandwidth case. All the primes greater than 3 now reside on the rows whose first values, or residues, are 1 and 5. These rows are the 2 residue tracks of primes. All the primes are equally distributed on each row, a property of all generators. This now reduces the prime number space to 2 out of the 6 rows, or 1/3 of all numbers. But notice what is happening. The rows that don't have primes are the multiples of the primordial primes, here 2 and 3. 1 and 5 are co-prime to 6, that is, they share no factors with 6, and their greatest common denominator with 6 is 1. So they are the prime generator residues for a bandwidth of 6. As we continue this process with larger bandwidth, we systematically eliminate from consideration all the multiples of the primordial primes and increase the residues that generate the primes, which continually reduces the number space that primes exist within. We are systematically squeezing the primes into a smaller set of numbers. Prime generators only use the residues that can generate primes for a given bandwidth. The modular complement and mirror symmetry properties are easiest understood visually. If we take an analog clock like this, the 12 hours are the generator's modulus or bandwidth. Notice the number pairs connected horizontally add to 12. They are modular complement pairs. For each, their modular complement is the modulus minus itself. So if you know the values on one side, you can easily compute the values on the other side and know their positions. But notice the pairs 11 and 1 and 7 and 5 are connected by solid lines and the others by dashes. That's because they are the residues here, that is, co-prime to 12, while the others are multiples of 2 and 3, the prime factors of 12. So as we cycle around the clock, we create new group values by repeatedly adding the modulus to the face values, like for military time. Now, when we cut the clock along its vertical axis and lay each half down flat, the residue gap spacing on the left and right are mirror images relative to the spacing between the bottom two odd numbers, which is the pivot gap. For bandwidths that are multiples of 4, such as 8, 12, and 16, their middle values are even, like here. So the bottom pivot value is 2. All other even numbers are multiples of 2, like 6, 10, 14, and their middle numbers are odd, so their pivot values are 4. All the primordial bandwidths have one factor of 2, so their middle values are odd, and their mirror image pivot values are thus 4. For the bandwidth of 5 primordial, or 30, we see here its 8 residue values, and their mirror image symmetry gap distribution around the middle pivot value 4. As the generator bandwidths get bigger, the residue gap structures include more and larger gap sizes on both sides, which occur deterministically. This mirror image symmetry property of the residue gaps creates the foundation for understanding the distribution of the prime gaps. We're now ready to define prime generators. Prime generators have the form shown here, where the value n is a prime number, such as 2, 3, 5, etc. Mod Pn is the generator modulus, or bandwidth. That is the size of the groups of numbers we break the number line into. K is the index value for each residue group as we cycle down the number line, and the Ri are the set of residues for the modular bandwidth. The modulus size is defined as the primordial of the generator prime value. A primordial is similar to a factorial of a number n, except where a factorial multiplies the sequence of integers up to n. A primordial multiplies the sequence of just the primes up to some n. The number of residues, or the residue count for a generator Pn, has this form, which are the primes minus 1 of the primordial. So for the generator P5, the modulus is 5 primordial, that is 2 times 3 times 5, or 30, while the residue count is 1 times 2 times 4, or 8. The residues come from the numbers less than the modulus, which are co-prime to the modulus, that is, their greatest common divisor with the modulus is 1. And again, the residues exist as modular complement pairs, which means once we know one, we know its complement. So we computationally only have to directly identify half the residues, and by this 2-for-1 property, we know the rest. There's an easy way to relate the modulus and residues count to the residue gaps. You only need to remember two simple rules, which I call the ruler rules. Here we have a ruler. The size doesn't matter, or the units. We're only concerned with the relationship between the gaps and the markings. So the first rule is the width of the ruler is equal to the sum of the gaps it has. For our ruler here, it doesn't matter which width sizes you use. Their total equals the width of the ruler. The second rule is the total number of marks on the ruler equals the total number of gaps. So if you use the numbers for the big gaps, each number marks the end of a gap, which holds for whatever gap size you use. The AI here are just the coefficients that hold the number of gaps for each unique gap size. In our case, our rulers, or bandwidth lengths, will only have even number gaps, So they will hold the number of gaps of size 2, 4, 6, etc. We can now use our ruler rules to set up our functional equivalences. Our generator modulus is equal to the sum of all the different gap sizes. So A1 is the number of gaps of size 2, which multiplied by 2 gives the total length of gaps of 2, which we add to the total length of gaps of 4 and 6, etc. We can write that in a functional form like this, where the primorial of the generator prime is equal to the sum of the gap sizes. And we see this interesting relationship, where the product of primes is equal to the sum of gaps. We will see this over and over. For the residues count, the number of residues is equal to the number of gaps, whose functional form is also a relationship between the product of primes and the sum of gaps. For the mathematicians and number theorists, where have we seen this before? In both instances, the left side is just a pure number defined by primes, and the right side a summation of real things, that is, residue gaps. We're now ready to understand prime generators. Here is the mathematical expression for the P5 prime generator. There are a few things I want to note. Before, we listed the first residue as always 1, which is always the first coprime value less than the modulus. I call those residues the canonical values for the generator. But as I explain in my papers, I always use the functional form of the generators, as shown here. I make the first residue the next prime greater than the primorial prime, here 7 for P5, and permute the position of the 1 residue to the end of the residues list, whose congruent modular value is now the modulus plus 1, which here is 31. Doing this skews the residue gap mirror symmetry off a bit, but as you'll see, it allows us to create a simple way to generate all the primes in consecutive order. Now P5 is the first primorial generator with more than 2 residues, but the last whose residues are all primes. All the larger generators will have some non-prime residues, along with all the primes less than the modulus. But as defined, prime generators generate all the primes. Can you see them? Can you visualize them from this expression? How about now? This one picture I consider one of the most beautiful pictures in all of math. It shows the property of prime generators that form the basis of prime generator theory you're looking at but probably can't see. This video is not the place to discuss them in detail, but I do want to explain in some detail what you're looking at. This is the prime candidates table for P5 up to the 100th prime 541. It contains the 97 primes greater than the 3 primorial primes 2, 3, and 5. It reduces the number space primes live in to 8/30ths, or 26.67% of all numbers. All the colored values are the non-prime candidates. What you're looking at is the result of the application of a very simple, efficient, and fast prime sieve I've developed, which use the properties of prime generators. Because this is the purpose of prime generators, to generate and then easily identify all the primes. Check out the resources provided here for the details on my prime sieves, including code to implement them. What we show here is we can take the P5's primes candidates table, which generates all the primes, and reduce it to identifying just twin primes. These are the 3 residue pairs that differ by 2, which will generate all the twin primes. This picture shows the result of the fastest possible algorithm to generate twin primes based on prime generator theory. The columns or residue groups without colored values show twin primes. Thus, using P5, we reduce the twin prime number space to 6 out of 30, or 20% of all numbers. We can reduce it even more using larger generators with more residue pairs that differ by 2. As with my prime sieve, you can read about the theory and application of my twin prime sieve from these resources. And here you can see code to implement my fast parallel segmented Twin Prime sieve done in these 6 programming languages. Here's P5's primes candidates table again. I stated earlier, if we have a list of primes, we can, by brute force, just observe the prime gaps and count them. So what I want you to do is count and record the prime pair gaps here, up to 541, the 100th prime. Now I just showed how to identify all the twins up to 541, except for the first 2, 3 and 5 and 5 and 7, the only instance of consecutive twin primes. There are 25 twins up to 541, so find the other 23 here. Hint, to find all the cousin primes, those that differ by 4, you can use the same techniques as for finding twins. So for those who are up to the challenge, pause the video and generate your results, then come back. Here is a table of all the prime pair tuples up to the 100th prime. Even in this small range of primes, you clearly see twins, cousins, and sexy primes dominate, which continues for all larger ranges. Now let's discuss prime generator sequences. This is a page out of my paper that goes into their details. A prime generator sequence, or PGS, is the sequence of the gaps between the residues of one cycle of the generator. Figure 2 is P3's prime candidates table, which only has 2 residues. When we write its candidate sequence out in a row, we see the repeating 2 gap sequence of 2, 4 for each cycle of the generator. Below that, we see P5's prime candidate sequence and its characteristic 8 gap value PGS. Things start to get a little more interesting now. Starting with P5, as a consequence of the functional residues form, the last 3 gaps in every PGS will have the form shown here of R0-1, 2, and R0-1, where R0 is the generator's first residues. This shifts the mirror image symmetry of the gap structure toward the front of the sequence a bit, with the pivot gap still 4. Since the PGS has much smaller values than in its candidate sequence, it may be computationally easier to use than the candidate sequence values, since it can regenerate the candidate sequence for any range, giving a starting residue value in the sequence. This is one of the useful purposes of prime generator sequences. We can now use the ruler rules to find the last piece in our prime gap Sudoku, the AI gap coefficient rules. Once we have a generator's prime generator sequence, we can determine the AI coefficients for each gap size it has. Equation 5 and 6 are our ruler rules equations written in terms of the gap size coefficients, that is, the number of gaps of size 2, 4, 6, and so on. In the middle of the page, which comes from my paper, we see the residues and PGS for P7, which has 48 residues and thus 48 gaps for a full cycle. It has 5 unique residue gap sizes of 2, 4, 6, 8, and 10, which corresponds to the values for coefficients A1 through A5. And below its PGS, we see equation 6 expressed in terms of these gap coefficient values, where here A1 and A2 are 15, A3 is 14, and A4 and A5 are 2, with their sum equal to 48 for equation 5. We have now fully characterized P7's functional equivalent form. So what we want to do now is determine the AI coefficient values from the PGS of larger generators and fully characterize their functional equivalent forms too. This page from my paper shows a table of the computer-generated AI residue gap values for the first 11 prime generators P2 to P31. This is another beautiful picture that visually displays more of the inherent properties that form prime generator theory that create the rules that govern the distribution of prime gaps. The first thing to note, per the ruler rules, for each column, the sum of the number of gaps equals the number of residues for that generator, and the sum of the AI values times their gap size equals the modulus value. So for the column for P5, 3 plus 3 plus 2 is 8, its residues count, And 3 times 2, or 6, plus 3 times 4, or 12, is 18, plus 2 times 6 is 12, gives us 30, the modulus value. Also notice as the generators get larger, that is, have more residues, you see this wave-like property of the gap sizes as you go down the columns, as the gaps go up and down in value like a wave with crests and valleys. As we'll see, this is also a fundamental property of prime gaps. Additionally, the number of unique gap sizes for each generator is on the order of the prime value for the preceding generator. So P3 has 2 gap sizes, P5 has 3, P7 has 5, and so on. So this data fully characterizes these generators, that is, identifies the number of their unique gap sizes and their values. But can we extract from it a way to determine all the coefficient values for all generators as they grow infinitely larger? In other words, can we find an expression for each gap coefficient that will produce the number of residue gaps of that size for any prime generator? So now let's crack the gap sequence code. Here are the first 2 rows of the previous table for P2 to P17. What do you notice? A1 and A2, the number of gaps of 2 and 4, are always the same and odd. But why is that? Well, the gaps at the top and bottom of the clock form of the modulus are 2 and 4, which is the pivot, and not part of the mirror image symmetry. So when gaps of 2 and 4 are part of the mirror image, they and all other gap sizes occur in even numbers, so one more from them make them odd. Now, I had created that table for an earlier paper, but never tried to decode it until I started writing this paper. And then one day I stared at it and started laughing because their structure was so simple. So can you see it? If you want, pause the video and try to create the really simple expression that produces these values for each generator. Okay, let's do it together. Now, there are really only 2 methods to try. We can look at the differences between the values and see if there's an additive pattern or a multiplicative one. Well, it's the multiplicative pattern: 1, 3, 5, 9, 11, 15. And how do you get that? Like this. That is, the A1 and A2 coefficients are the primorial of their generator prime minus 2, where 0 primorial is defined as 1. This fits the previous pattern of the gaps being a function of primorials. So now let's continue and determine the expressions for A3 and A4. Now these are a little trickier and have a slightly different structure, but still a simple pattern. The first value for A3, that is a gap size of 6, occurs for P5 and is 2. Here's expression where the coefficients on the right side are the coefficient values for the previous generator. So for P5, A1 and A2 are 1 and A3 0 for P3, which gives a value of 2 for A3 for P5. Check for yourself that this works for each generator. Now the expression for A4, a gap size of 8, begins at P7 and is even simpler. Pause the video if you want to try to figure it out. Okay, let's see the expression for A4. Again, check to see it produces all the values in the table. Hopefully you have now picked up on the pattern of what the other coefficient expressions are likely to look like. We see now going forward, all the coefficient expressions will be a function of some coefficient values from the previous generator and a factor of the current prime generator value minus some constant. Now all the residue gap coefficients can be written as recursive expressions. Here they are for A1 and A2, which are atomic gap sizes, as they are solely based on the generator's prime value and have no dependencies on other gap sizes. They are the fundamental building blocks for all other gap sizes. And residue pairs that differ by 2 and 4 are independent and will generate all the twin and cousin primes by themselves. Now, starting with A3, it's dependent on A1 and A2 additively, which is why residue and prime gaps of 6 are the most numerous. But there are multiple ways to create gaps of 6. You have those that come directly from residue pairs that differ by 6, and those that span two residue pairs that differ by 2 and 4. As we'll see, gaps that are multiples of 6 are dominant and play a fundamental role in the distribution of prime pairs. Now here's A4 again, which is only directly dependent on A3, and its values are even smaller than A1 and 2. But for A5, its values are greater than for A4, but smaller than for A1, 2, and 3. Now, so far we've seen the coefficient index value I subtracted from the Pn prime value as the factor for the previous coefficient of the same value. But for A6, that pattern breaks. To see why, go back and look at the data and it will become obvious. But for A7, that pattern picks up again. Now, I spent more than 2 weeks in July of 2019 sitting on my couch, sweating under a fan, manually trying to figure out these expressions. After A4, it became progressively harder. In fact, I almost had A8, but it broke down for larger generators. And then I decided to quit and go back to finally finishing writing the paper. However, I encourage people with the time and interest to go figure out more of these coefficients, which I suspect can be easily and straightforwardly done with the appropriate software, especially using AI. But we can clearly see every gap coefficient will have some deterministic recursive expression for its values, and they all increase in value for larger generators. And we also know the earliest possible generator a gap size can appear in by the factor Pn minus I, because it can't be negative. And thus, as the coefficient indexes increase, those coefficients can only appear in prime generators whose prime values are greater than they are. Now we have another way to predict when a gap of any size can possibly be first appear in a prime generator's PGS. This is a page from my paper where I tested these expressions for larger generators. I first computer generated all the residues and their gaps for P37. This took over 19 hours on my 10-year-old 2011 Lenovo laptop. Then, using the A1 through A7 values for P31, I verified the expressions produced the same results from direct computation. Then, using the values for P37, the middle table shows the expression values for P41 to P47. Now, R0 for P47 is 53, the first prime greater than 47, and all its residues between 53 and 53 squared are primes. So I generated all those primes and their gaps, and the table at the bottom shows the observed values for A1 through A7 in this region, and their estimated values based on the structure of its PGS distribution. As you see, the estimates are almost exact for every one of those coefficients. Now let's review the relationships between the gaps and the primes that we've seen. The sum of all the gaps is equal to the primorial of the generator prime value, which I explicitly write here as Pn minus 0 primorial, to introduce this nice general notation I've seen used that will express all our primorial relationships. The total number of gaps is equal to Pn minus 1 primorial. The number of gaps of size 2 and 4, Pn minus 2 primorial. The number of unique gap sizes for each generator is on the order of just the prime value of the preceding generator. So for P5, it will have 3 gaps, for P7, 5 gaps, and so on. And the number of new gap sizes for the current generator versus the preceding one will be on the order of the prime value for the preceding generator minus the prime value for the generator before that one. I stated previously that for us, the more relevant question is, can there be a finite number of prime gaps of any size? And the logic of prime generators answers that. To provide a comparative basis of how this proof works, We'll first review the simple proof attributed to Euclid establishing the infinity of primes. The key thing for both is to show their starting premises to be false by logical contradiction. Now, Euclid starts by assuming a finite number of primes. We'll assume our list starts with the first primes 2, 3, 5, etc. in sequence up to some finite Pn. We do the familiar thing and multiply them and add 1, forming an integer n. Now we know n is in fact the last residue of the functional form of a prime generator whose modulus is Pn primorial, and thus every prime in the list is coprime to n. This means n is either a new prime or a composite of smaller prime values less than n, but greater than the largest prime in our list. But this contradicts the starting premise that we knew all the primes. Thus, there must be an infinite number of primes because no matter how many primes we start with or add to the list, we can continue this process with no n. But this proof has limitations. It's a theoretical proof. It provides no computational or numerical answers to the question of is n itself a prime or a composite? And if it's a composite, it provides no method to factor it into its component primes. We can rectify these limitations using prime generators. But first, let's look at Euclid's method in operation and show we can fairly easily determine if n is prime. First, I want to show some simple ways to test for primes. Even in Euclid's time, and well back into antiquity, it was known how to determine primes. In particular, I want to show a method I created using simple math and logic, which I was never taught in school, nor have seen described in any book, paper, or video. In fact, it's so simple, it's hard for me to imagine ancient cultures didn't know it, but it seems lost to modern times. And it doesn't assume knowledge of any primes at all. All you need to know is how to count and multiply. In ancient times, they could probably test very large numbers in seconds using something like an abacus or even finger math. But first, let's see some simple quick ways to filter out non-primes merely through observation. Even numbers greater than 2 aren't prime and start with digits 0, 2, 4, 6, or 8. So by observation, we can eliminate 50% of all numbers from being prime and another 10% that are multiples of 5. Now we've eliminated 60%. Also, a number's digits that add to multiples of 3 or 9 is a multiple of 3 or 9. Try some numbers yourself and see that it works. So in a split second, we can look at a number and know if it's definitely not prime for over 60% of all numbers. What's left over, we can deterministically test using my multiplicative digits test. Now, every prime greater than 5 must start with odd digits 1, 3, 7, or 9. That's 40% of all numbers. There are 3 ways to multiply two numbers whose products begin with digits 1 or 9, and here they are. And 2 ways for numbers that begin with 3 or 7. I'll show how to use these simple relationships to deterministically test if any number is prime. Now again, Euclid's method creates values which are either primes or composites, which we'll determine using the multiplicative digits test, the MDT. Still, Euclid's methods can't generate all the primes in sequence, which we need to know to determine all the prime pair tuples. But we'll see we can do this using prime generators. To start, let's assume we only know the first prime 2. Applying Euclid's method, we create n equals 3, which we know is prime as it's the first odd number greater than 2. We repeat the process with these 2 primes. So now n equals 7, which we also know is prime because 5 is the only odd number between 3 and 7, and it can't be multiplied to equal 7. So we've actually found 2 new primes, and now know the first 4 consecutive ones. Using just the first 3, we get our old friend 31. Now the MDT has 3 pair test values for numbers beginning with 1. First, we do the 1 times 1 test and start with 11 times 11, which is 121 and greater than 31. So 31 passes that. The next is the 3 times 7 test. But since the digits for 31 sum to 4, we don't have to test for multiples of 3. In fact, we never have to use the MDT to test for multiples of 3 because we can use the sum of digits test for that. So we start with 7 times 13, which is 91, again greater than 31, so it passes that. Finally, we do the 9 times 9 test, which is 81, greater than 31. So it passes all these tests, and we know for certain 31 is prime. Using the first 4 primes, we get n equals 211, whose digits also sum to 4. We know 11 times 11 is too small, and 11 times 21 too large, so it passes that. Now 7 times 13 and 7 times 23 are too small, while 7 times 33 too large, so it passes that too. And finally, 9 times 19 is too small, while 9 times 29 too large, so 211 is also prime. Now continuing with the first 5 primes, you should now be able to use the MDT to verify 2311 is prime. But what about this? Using the MDT, you should have been able to find this. Here, 59 and 509 are prime residues for M13, whose modular complements are also shown. Now I did these tests by brute force, which can be optimized. We can limit primary factors up to the square root of the number and run multiple tests in parallel. Once you find factors, you can reduce them to strictly prime multiples. Thus, we can deterministically test and factor any size number by repeatedly using the multiplicative digits test. Now, whereas Euclid's method only proves the infinity of primes, we can use prime generators to do that too, but also identify as many of them as we want in sequential order. We start with the same premise Euclid used. We take a finite list of sequential primes and compute their primorials, which serve as their prime generator modulus. We then know all the primes not in our list and less than the modulus value are residues of the generator. But we also know there are non-prime residues scattered among them and don't know where they are. So to make life simple, we only look at the residues from R0 to R0 squared because they are co-prime to R0 and thus are prime. We now have a new longer list of consecutive primes from which we can create a new larger p prime of n generator whose modulus is p little prime of n primorial made from the new primes. And then from this new larger generator, we can extract a new longer list of consecutive primes between r prime of 0 and r prime of 0 squared. And we can repeat this process indefinitely to create as many new primes in consecutive order as we want. So let's see how this process works. Let's show the infinite progression of primes using prime generators. We start with using 2 as our known prime and create P2, which creates the sequence of odd numbers. Here R0 is 3 because for the functional form of generators, the last residue is its modulus plus 1. So we know between 3 and its squared 9, the values 3, 5, and 7 are primes. So here, 1 prime generated 3 new ones, a 3 to 1 nu to O primes ratio. And now we know the first 4 primes. Now we create P7, which has 48 residues. Its R0 is 11, and we see there are 26 primes less than 121 R0 squared, with 113 the largest. Thus the first 4 primes generate the next 26, a 6.5 to 1 nu to O primes ratio. We now know the first 30 primes and repeat the process. We create P113, whose generator R0 is 127, which generates the next 1,847 consecutive primes, a 61.6 to 1 nu to O primes ratio. Let's do this one more time. The last prime less than 127 squared is 16,127. Its generator R0 is 16,139, and we generate the next 14,218,065 primes, a 7,575 to 1 nu to O primes ratio. I call this process primal reproduction. Let's see graphically what this looks like. Here we see the progression of new primes we can create in one-step intervals with prime generators starting with 1 up to the first 50 primes. We know 1 prime generates the next 3 and 4 the next 26 and so on. So it starts slow, but by the 50th prime for P229, 5,307 new primes are generated, and it rapidly increases thereafter. The shape of the curve starts to look like a parabola, which we can see more clearly by flipping the data axes. Now we can better see a parabola-like growth curve for the new primes as we increase our generator primes by 1. This shows the growth rate for the nu to O primes ratios. For the first 50 primes, it looks fairly linear, but that's more an artifact of the limited number of points. The first 46 primes generate just under 100 times more new primes than old, and we're over that for the next 4 increases. But the ratios increases significantly after that. For example, using 100, 500, and 1000 primes produce ratios of 258, 1676, and over 3719. And we're still just using 4-digit primes for the generators. This just gives you a sense of the staggering rate at which the primes reproduce. Now that we have a method to generate all the consecutive primes, we can observe and record all the k-tuples between them. This table from my paper shows the number of unique gaps and their number of occurrences in the regions R0 to R0 squared. Since we know any prime P is R0 for a generator created with all the primes less than P, all we need to do is identify the primes from P to P squared, and we know they are the residues for that generator in that region. Here we clearly see, as P increases, so do the occurrences for each gap size and the number of unique sizes as the primes get farther apart. But also notice as P increases by factors of 10, the maximum gap size in the regions grow much slower. That's because these regions, P to P squared, represent a rapidly decreasing percentage of all the residues as the generator bandwidths increase to astronomical sizes. But hey, if you got the time, we got the primes, and can theoretically, empirically identify and record all the k-tuples that can ever be. So scanning horizontally, we know we only get more of each gap size. But scanning the columns vertically, we see the gaps have a wave-like property, producing crests and valleys. Let's see what that looks like graphically. This begins to show the characteristic heartbeat of the primes. We can see this wave-like flow of the ups and downs in the number of gap sizes, with crests falling around multiples of 6. This is data for the k-tuples for the first million primes. And when we graph it as a step function, this is what it looks like. But when we smooth it out, we see the characteristic heartbeat of the primes becomes very prominent, with the crest falling exactly on intervals of gap sizes of 6. Upon reflection, this makes sense, as gap sizes of 6 are most frequent, and thus also sexy primes. But this is still kind of non-intuitive, because even I thought maybe twin primes were the most frequent, but now we know. Now let's review the prime gap story created by prime generators. Gap sizes of 2 and 4 are atomic, and their residue pairs are the smallest and exist independently in equal odd numbers. Every other gap size is either between consecutive residues or combinations that span multiple residue gaps. Every gap size has a deterministic expression which computes its numbers. We've seen the first 7. The prime sequence 357 is the only instance of consecutive twin primes because they are the genesis odd numbers. And there are no consecutive gaps of 4, thus no consecutive cousin primes. Gaps of 6 are most frequent, thus so are sexy primes, and they can be consecutive. R0 is always a prime P, and the residues between p and p squared are prime and are increasing for larger generators, and thus their prime gaps are always increasing in numbers and in unique gap sizes, which are distributed according to the mirror symmetry property. And finally, there can be no last prime gap, as there is no last prime. We are now ready to answer the question, can there be a last pair of primes for any gap size? Hopefully, you should have at least strong suspicions on what this answer must be. So let's walk through the logic to answer it. Let's start by assuming at some point down the number line we hit the last twin pair. In other words, there are a finite number of twin primes. This means for some prime generator, it will contain this last pair, and every larger prime generator from then on won't. Is this logically and structurally possible? And if so, what happens to all the larger gaps in these larger prime generators? And if we can have a finite number of one gap size, can we have a finite number of other gap sizes too, or for every gap size? And is this possible when there are an infinite number of primes, which means there are an infinite number of prime gaps too? Now, claiming there are a finite number of twin primes, or any gap size, means mathematically in some prime generator, the coefficients for that gap size goes to 0, and remains so for every larger generator. But remember what a prime generator is doing. We are breaking up the number line into finite groups of numbers whose size is the modulus value of the generator. And within these groups, the numbers that are the residues, that is, co-prime to the modulus, generate all the primes in each residue group. And these structures are immutable. Once you pick a prime value for a generator, everything else is mathematically set in stone. So here is the relationship of the residue gaps and the modulus value. We can simplify it, since it's always even, to this. But this has physical significance, because the residue gaps exist with mirror image symmetry, and we only need to look at the first half, which contains the consecutive prime residues from R0 to R0 squared. And we know the total number of residue gaps is expressed by this. So if we claim there are a finite number of twin primes, then for every generator after they occur, the value for A1 has to go down to 0. But that's mathematically impossible, because we know for gap sizes of 2 and 4, the number of those gaps have a deterministic expression that is solely based on the value of the prime generator, and only monotonically increase in value for larger primes. So Houston, we have a problem. Generator gaps 2 and 4 only increase as the generator bandwidth increases, including in the region R0 to R0 squared, which we empirically know are all new consecutive primes. Thus, there can never be a finite number of larger gap sizes too, because every other gap size is dependent on gaps of 2 and 4, and can only increase monotonically for larger bandwidths. Thus, we see by the mathematical structure of prime generators, there are an unending number of prime pairs for any gap size n. Let's compare my work with existing research. If you look at the Wikipedia page for Polignac's conjecture, it lists a whole bunch of papers and references, one of which is Zhang's famous 2013 paper, Bounded Gaps Between Primes, in which the math world agreed that he had proven for some even value n less than 70 million, could be 2, 10, a million, 50 million. There exists an infinite number of prime pairs that differ by this unknown n. Subsequently to this, in 2014, the Polymath project reduced n to some unspecified number less than 246. So there, except for some number 2 to 244, there are an infinite number of prime pairs. Well, actually, they're right for every gap size less than 246, less than 70 million, and greater than 70 million, because hopefully you understand now, Polignac's conjecture is true. Now, I would urge you to look at Zhang's paper and others that try to explain or expand upon it. I didn't say read the papers, which are incomprehensible to most people. I mean, just flip through and look at them. What you will notice and not see are pictures. Just about everything I derived was based upon visual representations of these math structures. As I say, a picture is worth 1,000 postulates. If you want to get me, these are the best ways to do it. I generally check my emails multiple times a day. I also have a Twitter and Facebook account, which is the same as my email, but I hardly ever look at them. So if you really want to get me, these are the best ways to do it. If you made it this far, congratulations. Let me leave you with some closing thoughts. If you give me a number, I can tell you if it's prime. If you give me a prime, I can tell you if it can be part of a twin or cousin pair with absolute certainty. I didn't learn this in school. Take any size group of consecutive primes and they will multiply literally at astounding rates to produce more primes. But Fibonacci showed rabbits reproduce by using addition. So you start out on the single lane prime land highway, on your way to Grandma's, who lives at some faraway prime stop. Driving along, you see signs, next prime stop 2 miles, 4 miles, 6 miles, the most frequent, etc. And they get farther apart as you drive. And you have to wait for them to get close again before you can use the bathroom. But then you see P5 Expressways, which has 8 lanes, next exit, and you take it because you've seen this video and maybe even read the paper. So now you pay the exorbitant toll for the residue lane for Grandma's prime stop because you know now you'll get there in less than 1/8 the time. NASA spent millions trying to create an ink pen that could work in zero gravity. The Russians used pencils. If you keep doing what other people do, you'll keep getting what other people get. Think for yourself, but don't lie and think you know more than you really do. Knowledge is the assimilation of information. Most people can do that. But the ones you remember can use that knowledge in ways you'd never consider. Thanks for watching. I hope you had fun and learned something too.